website, you'll notice there is a job board very specific to Lunchalytics Edmonton. There's another one in Lunchalytics Calgary. So if you have a posting and you'd like to post to this group, that's a great place to do it. And if you're looking for a position, you can look. I'm not sure if there's anything posted. Probably not. But that's a great thing to take advantage of. Speaking of Reese, who I was speaking of, he's going to give us a 2-minute announcement about something very exciting coming up from our great sponsor, ATB.
So there is a conference happening at the end of October, so October 28th to 30th at the Edmonton Rec Center. So it's Spark 2019. I think the theme they said this year is carbon positive. So this conference is hosted by the Emissions Reduction Alberta organization, which is like a cross-industry organization that's helping out with getting Alberta to hit its greenhouse gas emissions target. So this is obviously very contentious stuff in the news, but the good news is at this conference they're hosting a data-thon. So ATB is helping out with this data-thon throughout the conference. And I'll read you the blurb that some marketing person put together because it'll sound way better than me trying to just wing it. Industry experts and data scientists are teaming up at this conference to uncover how data used the right way can help solve some of our toughest problems. So ETB's AI Labs, that's why I'm here, will host the hackathon on site at this conference during the duration. So we're going to have data teams from the U of A, Amy, and any other groups that are interested working in real time to solve the environmental challenges facing our oil and gas industry. And then at the end, they're going to have a 75-minute session where they pitch all of the different teams' kind of hackathon outcomes, and people are going to be able to vote on the best solution, and there will be a winner with prizes. So essentially, if you're a data scientist or an analyst or a developer, and you're interested in looking at some like oil and gas operational data to do a little bit of data for good type work on trying to think of ways to solve some of our emissions targets, come talk to me afterwards and we'll swap information, and then I'll provide further follow-up details, and maybe you can come join the team and be part of this oil and gas hackathon that's coming up. You know. So thanks so much for your time. Enjoy the other two talks here coming. One last quick announcement. Actually, just a query of the audience. How many of you
Are academics or researchers, like you're affiliated with a school of some kind? All right, we have a handful. How many of you are students? Like students, okay. Okay, we'll lump you together. How many of you are decision makers, but you don't like get in there and write code and do analytics? You're kind of like a manager of analytics type, okay? So we have a handful of those. And how many of you are practitioners? You actually do this for your day job. You make charts and graphs. Cool. That's great. Okay, those of you who might be interested, I do teach a course at the U of A called I forget what it's called, but anyway, it's the OM course that does real live consulting projects. If you have a project, you're a company, and you say, hey, you know what, I'd love to have an analyst do like some students do a project for me, and it's nice and containable and quantitative, like analytical, come talk to me, and I can hook you up. It's the prices start at $5,000, but you get access to some of the best students, and they get access to some real data and real life. It's a beautiful ecosystem of things. So, anyone participated in that before? Just give me a little wave. So, a handful of you have. So, it's great. Afterwards. All right, I think I'm done killing time. Are we ready to start? Okay. So, without further ado, I would invite Evan from AB. I invite Andrew from the City of Edmonton to talk about something very, very exciting. Andrew?
No worries. And is this mic working? Oh, okay.
Turn it all the way on. Turn it all the way on.
All the way.
F2, yeah.
F2?
Yeah,
That
now
works
it's
now?
working.
Okay. Thank you. So I'm Andrew Reed. I'm a project engineer at the City of Edmonton. And I started with the city last February to participate in the completion of the Climate Resilient Edmonton strategy. Now, many hit and miss whether people are kind of aware of the different angles of management of climate change, but there are two different sides of the equation, as I like to say, because I'm an engineer. the mitigation side, which I think everyone is rather familiar with in terms of our contribution to climate change from the greenhouse gas emissions that we release. So that's really looking at what causes climate change, whereas the adaptation strategy that I was part of is really looking at how the climate changes and how those impacts from those changes will affect us, whether for positive or negative. So it's really managing both sides of those equations, and while there has been a lot of attention and focus on that mitigation side, especially here in North America where we do have a high GHG per capita release, there's been a lot of focus on that, but it's always good to remember the other side of the equation, that we're looking after ourselves, that we are protected from those weather systems and those massive changes in climate that are expected. To put that strategy together, the city put together this project team. I came in at the last year of this 3-year investigation that basically went through and identified all the current climate hazards that Edmonton experiences and have experiences to date, and then looked at the future expectation of how those changes would likely occur based on the modeling that has been done. We then had our expert assessments and expert operators from the city look at what those impacts mean for every specific operation within the city, as well as looking to the broader community and inviting the broader stakeholders to look at what that information is and evaluate how they might be affected. And then identifying those key vulnerability areas where Edmontonians are more vulnerable, and where there is a need to prepare better for those changes. So it was a very all-encompassing process and involved a lot of rigorous assessment of climatic changes and modeling, as well as bringing together a very diverse sort of stakeholder group to tease out, what does that really mean to someone that's operating a specific piece of equipment or a specific city program or a business. And so this was completed and presented to City Council November last year, and we've started implementation in this year. Now, going into that, we obviously had that baseline historical data that we wanted to look at. What we had available was the record that has been collected by Environment Canada since 1840. It had sort of limited coverage in that period. I think it came into Edmonton around the late 1800s, where the record starts, and then kind of fully expands throughout the 1900s. Using that hourly weather conditions that are collected at those stations, the data set is actually adjusted and homogenized to deal with any station moves throughout that long time period, any adjustments to instruments, because clearly we're using different instruments than we had been in the 1800s, and any operating practices in terms of how that station has been operated. So there's a lot of work that Environment Canada does to create a data set that is reflective of that full time period. And of course, every single station that this is recorded at can be influenced by local factors. Landscape changes, as I said, station moves and things like that can affect what is actually reading on that meter. Ideally, if we had full data accuracy, we'd have a station every millimeter everywhere. But reality is that we can't have those sorts of systems, so using what is available. So I'll beg the question here as to what station you think measures Edmonton's climate best. The picture there on the left shows the blue dots. That would be stations throughout the region, but what do you think would be the best station to take it from?
Probably Blatchford.
Blatchford, you figure? So, sorry?
Buford.
Buford? So all of them actually. You take a look at all of the stations, statistically compare them to identify if there are key outliers that have data that doesn't work for integrating with the other stations. Do your statistical analysis. I was quite surprised it wasn't an area that I was familiar with when I got into this work, but the amount of rigor and statistical analysis that goes into defining a good climate data set is intense. It's not as easy as picking up a station, the data at a station, doing your plots and taking a look at it and inferring from that. There is far more interpretation that is necessary that involves both heavy statistics as well as climate scientists involved along the way. So that was a big eye-opening experience as to how difficult this really can be, and how much effort has been put in already from the federal government in terms of providing that adjusted and homogenized account. That already is a huge step forward in terms of providing that data set. But then taking that data set, making it applicable to a specific location in a map rather than a general region requires a lot of effort. And so what did we find? So this is a plot of the average mean daily temperature historically. And you can see over the last 100 years, the trend line there is about 1.7 degree Celsius change per century. And just for context, if you look at a shorter time period, that 50-year time period, we can see that that trend has actually escalated to almost double that rate. Now you'd have to do a lot more analysis to see, how that is changing within that. But in general, this has revealed that Edmonton has already experienced climate change. We've already experienced a 1.7 degree Celsius change over the last 100 years, and a 3.5 degree Celsius change over the last 50 years. And that was found to be even more stark when we looked at winter temperatures. So this is average mean daily winter temperatures over that same time period. And you can see that the trends are almost double. And that's been, I think you've probably heard from media recently that Canada is warming faster than other places in the world. That is absolutely what we found when we looked at our investigation as well. And it is because of how we are losing that deep cold winter period. And obviously these are all on averages, but losing those extreme colds and that sort of trend in the winter is where we're seeing those temperature swings the most. So, what is that historical data used for? Well, this is where my engineering brain kicks in, and I look at all the design and building codes and construction codes that are out there that all rely on these weather data sets that are all historically based. The underlying assumption of that is that the past climate is the same as the future climate. And I think we can all agree that that's not the case. People want to disagree on what the cause is, and that's fine, but we can definitely agree in regards to adaptation that the climate is not the same. It won't be the same in the future as it has been in the past. So we know that this is false, and we know we need to address this information gap as to how we need to change how we're building in the future. So then we started looking at the climate models and what those start to show. So getting into that, we had our baseline period, and this is I like looking at average temperatures under this bell curve because it relates to the statistical sort of method that goes along this in this normal distribution. And we know that the average annual temperature in Edmonton is about 2 degrees. But when you think about what that means in terms of all the data points within that data set, well, we have this normal distribution, and that means you could have, a year on the historical record that would be, below 0 as an annual average, and up to, 5 degrees Celsius as an annual average. It's been bouncing around in there within that period for some time. Then you look at the climate models, and what we're expecting from the temperature shift there is we expect this average annual temperature to increase to fall more along the 5 degree mark. And this is in the 2050 period. So what that means is that whole bell curve is shifting upwards. And so where we see the annual average temperature of 2 degrees that we've been feeling in historically, we're well prepared for that. But where we see annual average temperatures reaching 7 or 8 degrees, those are temperatures that we've never experienced. We don't know how infrastructure necessarily will respond to these sorts of temperatures, the cooling demands, and those sorts of things. So that's really where, again, those vulnerabilities lie in our climate and how we've built and designed our systems. So thinking of that in terms of sort of a time series, we have our historical observed temperatures, again, on that temperature record. And we know, again, from these climate models that we know the business as usual is going to take that average annual temperature up to about the 5 degree mark. That is along a business as usual trajectory where we do not take steps to reduce our GHG component. Obviously, there's a lot of effort going on to try to address that aspect and push us more towards this strong mitigation pathway. But what's important to note here is that this strong mitigation pathway, which does include a lot of significant efforts to decarbonize, you can see that we're still seeing an annual average temperature increase of 5 degrees. So even if we are hugely successful in all of our decarbonization, there is a climate change that's going to occur, and we need to address it in terms of how we build and design our systems. So this is really where the adaptation component really lies in. And then that obviously, getting better information around how that climate is changing is going to be heavily reliant on climate modeling and the ongoing updates and refinements to these models to make them as accurate as possible so that we can rely upon them. So the climate models are incredibly complex. I can't say that I've worked on one myself. I'm not a climate scientist or a modeler. I work in air pollution, so I know some of the physical chemistry and the physical factors that go into it, but I've never compiled an entire sort of climate system before. But it's all based on numerical models and physical laws that break it down into these little segments, requiring supercomputers to do all of your mass and energy balances through those, and all of the numerical methods that I've long forgotten from university and would have to remind myself about. And we know that, and we have a number of different organizations doing different models for different purposes. They all are purpose fit to define specific key factors that they are interested in. Some are more interested in precipitation, some are more interested in temperature, and those sorts of factors. And so there's ongoing effort and expertise needed to define the correct model and for the right purpose. And that is why the City of Edmonton has been working on, through our implementation this year, establishing our sort of access to the climate modeling that exists. So you'll see that this is showing annual average temperatures again on the chart. The green line is representative of the measured data set, and then we see the business as usual, as well as the significant reduction sort of pathway there. And this is being set up so that we can get access to all of the suite of models that are applicable to our region, look at how those models fit the real data sets from the measured results, and allow us to determine whether or not we want to use a certain model to inform our design or our plans, or determine how we want to change. So as we move sort of into the other functionality of this system, when we look at trends in probability, we can start to look at how comparable these models are. And I'm just going to step out here because I think it's easier. But so here you can see this is our measured data set. And ultimately what we want to do is determine on the two representative concentration pathways what are the best models for this data set. And we can see that we get a similar standard deviation for models 4 and D. And even though the trend is a little bit different, we know that they are falling within that variability pretty well. And so we can then do further investigation on these models, determine if they will be right for us to use in terms of forecasting future temperature changes and how those would incorporate into building designs. And what I think is most useful, and this is just me applying my engineering skills, is this sort of threshold analysis where we can define a specific threshold. I've just put an example of 5 degrees in here in terms of the annual average temperature. And we run the system, and it tells us through all the models that are being looked at when exactly that annual average of 5 degrees, when that probability starts to increase, that we would exceed that. So you can see for the two models here, RPC 4.5 and 8.5 being the two GHG pathways, somewhere within the 2030 2040 time frame, we can expect that annual average temperatures will start to hit that 5 degree mark. Now, then we can take that away when we're looking at city infrastructure or design standards to say, well, okay, this building has been built to last 40 years. Will we have to do a major retrofit to deal with the cooling requirements due to these temperatures? And so we can start asking those questions and determine the time frame in which retrofits or change outs of equipment, or basically determine when systems that are in place right now become obsolete and would require investment to upgrade and address. And so this is when we get to really start to look at how we actually deploy capital to resolve these vulnerabilities in an effective manner, and allows the city to do that planning. I will say that we've only just set up this program and we have not trialed it in any way on any infrastructure yet. We are still working through the system, and we will be trying to apply it on some specific sort of investigations here and piloting it for the system. But ideally, if those all go well, we will have this system in place that we will be able to deploy citywide, and we can evaluate any infrastructure designs against how they will withstand future climate changes. Which is important because if you hadn't heard, the City of Edmonton has declared a climate emergency at the end of August that also requires the city to revise the community energy transition strategy to align with a local carbon budget to meet a global temperature increase of 1.5 degrees Celsius. I've actually just been pulled away into this work, so I'm actually being drawn into the update of the GHG plan and looking at what it would take to meet a sort of these global commitments that had been made on a city scale. And so through that, there are these 6 climate shifts that have been defined, looking at everything from the tools and targets, so how we budget, how we incorporate carbon into our budgeting processes, and how we ensure that we're meeting those global carbon budgets, as well as looking at how we get to zero emission transportation and being a low carbon city, targeting buildings specifically, because obviously heating and cooling are major energy components that we will have to address in our buildings if we want to meet a net zero standard. Unleashing the renewable revolution and trying to take advantage of all the renewable opportunities that we do have as a city, or even outside of the city if it's necessary to kind of look at that way. Incorporating sort of justice and equity into the transition, so making sure we're remembering about our senior citizens, our homeless, and any other vulnerable populations that might not be as able to sort of participate in this shift, making sure we're not leaving anyone behind. And then, as I like to call it, the emergency sort of parachute on the back end is these negative emission technologies, looking at how our forest can enhance its carbon uptake, as well as technological solutions in terms of carbon capture and storage or direct air capture, and how those fit into this mix. Ultimately, when we look at the technical details along these shifts, there's still a significant gap between those GHG expectations and where we need to go. And so there's definitely some component that is going to have to be taken up in terms of negative emissions, either through vegetation or direct technology sort of application. And so that's kind of the step forwards now at the City of Edmonton, is looking at this GHG plan and how we incorporate both the adaptation components as well as the mitigation components, and bringing that all forward to council next year. I think Q3 is when that whole plan is supposed to be presented. So yeah, some pretty incredible timelines to get a lot of work done. But with that, I can take any questions or comments or anything.
Thank you so much for the talk. Fascinating. Yep. Really glad that City of Edmonton is having this initiative and recognizing the risks. My question is that, at least from my personal observation, it's not that I notice an increase in the temperature that much, although it definitely happens, right? But it's that the climate becomes somewhat more extreme. I see so many extremely cold days, or extremely hot days, or like rain, or you name it. I mean, I think we all remember. I think in the past few years, like in February, it's been like a trend that it would rain heavily. Basically, all the snow got frozen, so the skiing season is kind of compromised. Yeah. So that said, average temperature may not be the best metric to capture all these extremes, right? So perhaps you could think of a better metric, like maybe look at, I don't know, certain like 95 and 5 percentiles of the temperature, see how that changes. I think you would see a much more extreme picture than just looking at the average.
Yeah, and I should say I picked that average temperature as just an example for this room. Okay. It was definitely not intended to infer any specific component. When we start looking at what those vectors are, I'm actually looking at the construction standards and what weather components have been included in there. There is historical weather data sets that are incorporated in the building code. So comparing, what those standards are versus what that future is, and then creating that same data set for the future cast, then could get incorporated in the building code. Now I'm getting very ambitious that would happen down the road at some point when that data set is solid and could be sort of incorporated that way. But absolutely. In fact, I think if I can go back, you can see on this little piece here, and this is a scrollable window. These are all of the different factors that we can take a look at. So hottest days, ice days, lowest minimum temperature, precipitation over one day. So there's actually a number of factors we can take a look at. And each one is going to be different for every infrastructure to some degree, depending on what is of utmost importance. So not just going to look at that average temperature, that's for sure, because that doesn't help me design a building, because what I need to design that building for are the extremes. Yeah.
One more question. Saw that hand in the back.
As far, have you guys taken a look at things like modeling the water supply from the North Saskatchewan River, since we're quite dependent on that for our water, like say 50 to 100 years from now?
Yeah, so a lot of that work is actually led from EPCOR, because they're operating the potable water system there and the water supply. But we did look at water supply from the component of the GHG factors, or the forecasting that we had. It's incredibly complex, driving from that climate system down to the river system. And I know EPCOR has been building it from the river system up to get to that level. Right now, from my understanding, EPCOR is far more concerned about contamination making it into the river upstream and affecting the water supply there than actual like running out of supply. But I will say that they have identified that is a risk, and we're definitely pushing them to evaluate that further and further, so that we know when that might become a real tangible risk that we need to take a look at. We have a lot of research from like David Soshin and whatnot that are showing that the variability of flow in that river is quite incredible when you start looking on longer time scales than just the recorded history. So that is a huge concern, is whether we're going to be moving into a really extreme drought period that we've never even witnessed as since colonial settlement time. Those are types of things that we've never had to address yet, and so that is part and parcel of the plan. How it gets prioritized and how that interaction is between EPCOR is kind of the challenge. So right now we're very much dependent on their work, but it's up top to priority for my team anyways, in terms of what that looks like. And we're keen on how we look at conservation outside of the city of Edmonton to maintain that river flow, so that we're not short in 20, 30 years or time.
All right. Well, thank you very much. That was a great. I did like the part where the winters got warmer, though. That did help my heart. We now have Evan from ABMI, which stands for the Alberta Biodiversity Monitoring something Institute. That's great. So take it away, Evan.
Hold on. Sorry. 1 minute for technical difficulties.
All right.
Dan can tell a joke.
Okay, let's do a contest. This is really fun. I bet that there are two of you in this room with a birthday on the same day. Guaranteed. Anyone with July 19th? That's my birthday. No? Okay, say your birthday, starting here.
August 23rd.
Raise your hand if it's the same. January 5th? Oh! So this is a good way to make money. When I teach at the U of A, I do this, and I make lots of money. I bet the students 20 to 1 odds. Usually there's like 200 kids in the class, so it's like I could go 200 to 1 and still make good money. But everyone takes the bet, and they're always shocked when I say, I'll offer 20 to 1 odds, and I start pulling out 20s, and they start throwing their loonies and toonies, because I put a max bet at 2. Otherwise, they'd give me all their savings, and we pile it up. And then when, I ask the first person and someone raises their hand, usually, and then I just scrape all the money into my pocket and walk, and they're like, he's keeping the money. Yes. That's how you learn. All right, so Take it away, Evan.
All right. I'll get started then. So yeah, my name's Evan Delancey. I'm a spatial data scientist with the ABMI, and now you know what the ABMI stands for. So I'll be presenting a little bit on wetland prediction using machine learning and earth observation data. So quick intro into the ABMI. I'm assuming most of you don't know who we are. So really, our goal is to track changes to wildlife habitat across the whole province. And our operating principles really are we're independent, we want our data to be scientifically credible, and really transparent data. So all our data is available online, and really you can see our methods. So the main people that are going to be using this data are land managers, our land use decision makers. These people can use our data to make good decisions about how to manage all Alberta's land. All right, so I'm going to get into the project I'm going to be presenting, or the analytics we do with this. This is our mapping and monitoring of wetlands across the province. So that's a wetland there, the light green part. So this is part of our advanced land cover prediction and habitat assessment program. Really the goal of this is to essentially just map all of Alberta, map all this land cover across there, and also monitoring the changes. So the goal, simple yet maybe ambitious, is map the location and extent of wetlands across all of Alberta. So how are we going to do this? You could go and visit all these wetlands, but Alberta is huge, very remote, so you can't really do this. You can do this maybe for a select few. You could also fly airborne imagery for the whole area. That's probably expensive and would take a lot of time. Probably the best thing if you're trying to map a large area is to use earth observation or satellite data. So for this, we can get freely available 10-meter resolution data, essentially for the whole province. So this is what we're going to use to do this, and then to actually get a prediction across the whole province, we're probably going to need to use machine learning or modeling methods to get an accurate prediction of where wetlands are across the province. So wetlands, just so everyone knows what they are, you probably want a quick definition. Essentially, they're low-lying areas that are covered with or saturated with water long enough to support aquatic plants and animals. So while these are important for ecosystem services like flood remediation, water filtration, lately they've been of particular importance or particular interest just due to their carbon budgeting. So in certain wetlands called peatlands, you have really thick deposits of peat moss, and these are going to store a ton of carbon. So not only are they going to store carbon, if they're disturbed, then you're also going to be able to, or it's going to release a ton of carbon from this area. So that's why this is of particular importance. So not only do we want to know where wetlands are, we also want to know what kind of wetland it is. So you can see at the bottom here, separated that wetlands and uplands. Uplands just mean a forest or something. And then it goes into organic wetlands, mineral wetlands. Organic wetlands are these peatlands, the ones that store a ton of carbon. And what we're going to look into later is the bottom line. So bog, fen, swamp, and marsh. Bog and fen, these are the peatlands, they store a ton of carbon. And we're also going to look at classifying swamp and marsh. So the data for this, as I said, satellite data. So number one, we're going to use optical data. That is essentially your red, green, blue, near infrared, short of infrared, so wavelengths of light that you observe. We're going to use the European Space Agency's Sentinel-2 dataset, or Sentinel-2 satellite. So this is going to be 10-meter resolution across the whole province, revisits the whole province pretty much weekly. We're also going to use synthetic aperture radar data. So this is when you're shooting radar at the ground and measuring the backscatter of that. Great thing about this is it sees through clouds, as you can see in the animation there. So when it's really cloudy, like it was this summer, you're not going to get much optical.
Tech guys just go up and
No, but it's like I have to walk through like over people's legs and stuff.
Let me help.
Time series applications, how things are changing. And the last data set is topographic. So this is just the elevation of land. So this is really important for finding out where wetlands are and their form and function. So with elevation of land, you can essentially just model how, say, wet this ground should be based upon topography. So if you dump water on there, an even amount of water on that landscape everywhere, water's going to drain and pool in certain areas, so probably it's going to drain in that flat valley in the middle there. That's probably where your wetland is going to be. Those other slopes are going to shut off water, and you're not going to have a wetland. So now that you know the data, we can kind of explore this data. So we have our label data. So we're going to explore this label data with 3 classes. So we have wetlands, we have open water, and we have uplands. So can we actually differentiate these classes with the data we have? So the first one, the top one, that is topographic wetness, SWI. It's just a different name, but it's topographic wetness. So open water, water is of course wet, so we'd expect it to be very high in value there. Wetlands, of course, are wet as well, or more wet than uplands. So we're seeing good separation of classes there. REIP, that's essentially a measure of vegetation productivity. So for this upland, when we're in the boreal or northern boreal areas, we're typically seeing uplands as forest area. So these are going to be more productive, and then wetlands are going to be less so. So again, we're seeing good separation here. Open water, that's not a great indicator for open water, so we won't worry about that. So when we plot it in 3D scatter plot, we should expect to see clustering of these classes. So open water, being navy, is really separated with our radar backscatter. So that's VVS1 there. Radar is great for sensing water. And then uplands and wetlands are really separated based upon their topographic wetness. So we see good clustering there. And then NDVI, again, a measure of vegetation productivity, is helping us separate water and also giving a little bit of information to uplands and wetlands. So we're going to input about 10 of these variables into a XGBoost prediction. XGBoost is just a machine learning algorithm. And then we're going to get a probabilistic prediction of where wetlands are. So high probability wetlands are the dark blue. Low probability or high probability of upland is in the brown. And then we have open water in the navy. So as you can see, those low plains there, which water is probably going to drain into, we're getting a very high probability of wetlands in that area. And then anything with a slight slope, really, is probably going to shut off water. We're not going to have any wetlands there. And then also, we're seeing the lake there predicted fairly well. So this is doing well across about 60% of the province at a 10-meter resolution. So at a pixel level, we're really predicting wetlands very well. So yeah, we can map out wetlands, uplands, and open water, these 3 classes, with high accuracy, so high 80% across 60% of the province. So this is at a 10-meter pixel level. Next step, can we actually distinguish wetland classes? So within those wetland, within those wet areas, can we distinguish these bog, fens, marsh, and swamp at a pixel level? So the label data here is on the right. So we see bog in light green, fen in tan, marsh in brown, and swamp kind of in olive color. So this is our label data. So we're going to see what the Earth observation data actually tells us about these classes. So to me, not that good. They all look identical at a pixel level, really. In topographic wetness, they all look the same. Marsh is maybe a little different. We have vegetation productivity from our optical data. Our radar data is saying everything's pretty much the same, even seasonal metrics. So at a pixel level, these classes aren't really any different. So we're not really going to be able to run our XGBoost model. So if you look at this in the 3D scatter plot, no clustering. Maybe marsh has slightly more outlier points, but bog, fen, and swamp are pretty much all the same according to our Earth observation variables. So our pixel-based shell learning XGBoost algorithm probably won't work. It might just be four-sided dice roll to see what classes. It doesn't actually have any information on what class it should be. So our solution for that is to use segmentation convolutional neural nets. So this can hopefully use more contextual information or the texture of certain wetlands. And the hope is that certain convolutional filters might discover unique characteristics of these wetland classes that aren't really coming out at a pixel level. So just so you know what we used, so we ran it, it's a UNet convolutional neural net architecture. Oops. Back. So we're training on a patch level here rather than a pixel level. Before we were training on just a single pixel level. Now we're training on 4,800 patches of label data. They're going to be 224 by 224 and 16 depth, which means we're using 16 input raster Earth observation layers. So when we get this, another 3D animation, so we're going to zoom in. So the first thing to me is these look like really good ecologically meaningful shapes. So sometimes at a pixel level, you'll get a very salt and pepper look. This looks very clean. We'll see the tan and light green here. That's a peatland complex where you have fen and bog in the same area. You're also seeing swamp there, often associated beside streams, and even marshes, which are really just seasonally flooded areas. So this works pretty well across 75% of the province. Even does well, or very well, with upland and open water. As you can see, any area with a slight ridge or something is predicted as upland. All right, so the results. So we have 86% accuracy overall. So that's across 75% of the province, so that's pretty good. When compared to a pixel-based model, or a pixel-based XGBoost model, the CNN model definitely outperforms this. And in the graph, you can see an F1 score measure. That's per class. So that's essentially how well we're predicting each class. So open water and upland really are about the same in here. As we saw before, we can really predict open water and uplands with just a simple pixel-based model. But where it differs is within the wetland classes. So for fen and for marsh, we're getting a much higher F1 score for the CNN model when compared to the XGB model. So the XGB is in orange right there, and the CNN is in blue. So why do we think this is? So if we zoom in here, I'm thinking there's certain convolutional filters which are picking out the texture of these classes. So for example, fen has distinct flow lines usually. So fen has flowing underground water, or in the groundwater, it has flowing water. So that's why we have flow lines in here. So I'm thinking these certain convolutional filters are going to detect these parallel flow lines and then predict a high probability of fen. Marshes are often associated around lakes. So I'm thinking here a certain convolutional filter has a edge detection filter, detects the edge of the water, and then we get a high prediction of marsh. So I'm thinking that's why these two classes are so high. Swamp and bog maybe are having more trouble because a certain convolutional filter can't fit. We can't find a unique feature of this. So project conclusions. So wetlands as a whole can really be distinguished from other habitats, open water and upland, with a fusion of Earth observation data in optical, SAR, and topographic data. So this can be done at a 10-meter pixel level. Wetland classes, so our bog, fen, marsh, and swamp, cannot really be distinguished from one another on a pixel level. So the data just really isn't there. So really, I think you need to use segmentation neural nets to better capture natural complexities of complex land cover types. So wetland types are pretty complex land cover types. There's not a ton that's differentiating them. So you really need to use segmentation neural nets to really better capture the complexities here. All right, so thanks to the Lunchalytics team for the invite to present. And of course, thanks to other ABMI staff who helped out with this project. If you're interested, we do have an hour-long webinar online. You can hear more about this. And if you want to download our data, the wetland data is freely available online. So if you want to see where wetlands are in the province, then definitely take a look. That's it for me.
Any questions? Yes.
I'm curious about the developing the ground truth data set. How did you go about the labeling process? Can you speak about that a little bit?
So that is right now a team of about 5 people doing photo interpretation of like 30 centimeter imagery. So it's like 3D, they interpret it. And there's like 800 sites across Alberta. So we're trying to cover about 5% with this label data. So yeah, it's a pretty big label data set. Yeah, highly detailed. I mean, it's even more detailed than bog, fen, marsh, swamp. It'll be treed, bog, I mean, graminoid, fen, things like that. So the label data is, yeah, tons of it. And yeah, a big team of people produce that data set.
Have you actually, have the results from this modeling led you to find any new wetlands that were not known before?
I think so, in terms of when we're using topography. Sometimes when you're looking from above, you have no clue it's a wetland. It might be flooded underneath trees. So if we're using topography to model where wetlands are, you should see pooling in these certain areas. And if someone's looking from above, a photo interpreter, they might not have a clue, say it's a swamp that's actually flooded. We don't have necessarily evidence yet, but I'm assuming we found some new wetlands that haven't really been discovered before. But I mean, yeah, no evidence there, but I would think we would find some just because we're modeling it based upon a DEM.
Hi, because myself, I have done a wetland project too. I developed a machine learning model. If you tell me a polygon and a DEM of a wetland, I'll tell you how much water it holds up. So for me, because I have seen your data is published on the ABMS website, I was surprised you use the word predict. But to me, it looks like you are trying to interpret the satellite images to its land use, if it's a wetland or not. So have you? But the word predict make me think about the future time series data. So have you done anything about future, like predict this kind of pixels, if it's going to be a wetland in the future or not?
Yes, we have thought of that in terms of climate change data, certainly. Say if it warms up and there's less precipitation, you could theoretically predict where a wetland will be or how it will dry up. So it's essentially just like modeling a bowl, have filled it with water, and then more water might precipitate, it might get hotter, less precipitation, so it's slowly going to dry out. I think we have thought of that. That's a little more complex. We want first a really good baseline of where wetlands are. If we can get that, then I think the next step is moving forward and predicting in the future, as you said. No, in the future, maybe a few years, I think.
All right, another question?
How easy do you think it will be to apply this model to other provinces or other areas of the Earth, I guess? And is that something you want to do?
Yes, so within Canada, I think that's definitely something we want to do. So, I mean, the boreal forest region in Canada is pretty big. So this work was mainly done in the boreal region, and wetlands are, I mean, they're different across the whole province, but they're relatively similar. So there are some studies we're working with other people to do a prediction across Canada. Doing it, say, in a mountain region is different, and then doing it in the prairies here, wetlands are completely different, so you'd have to run a separate model. But I mean, I think this is applicable to anywhere in the boreal forest, so that could be Europe, Russia, anywhere in Canada. If you have a good model of what certain wetlands look like, then definitely I think it's applicable. And yeah, the data would be exactly the same, because it's the same for the whole world, the satellite data.
Any last questions? All right, I was trying to stall you guys just a little bit because the food is still not yet arrived. But I'm out of jokes. Thanks so much for the talk, Evan. Let's give him a... And hopefully you will stay and socialize for the 2 to 5 to 10 minutes it'll take for them to deliver the food. Trust me, it's going to be really good. Oh, we do have a question. Yeah.
So I've maintained for a long time that burning scotch ruins, or burning peat ruins good scotch. I mean the environment. So that's correct.
That's right. No, it's all right. That's That's it. Go talk amongst each other.
Hold on, before you go, just a reminder of like our little procedure. So before you leave, if you can help us stack the chairs on that wall, because Lunchalytics does need to put this room pretty quickly for another meeting at 1:30, or sorry, Start Edmonton does. And the second thing is, if you would like to speak, that would be great. We're still trying to put together the kind of framework for the next few months. So if you're interested or have someone that you think would be interesting to speak on these kind of topics, we'd really appreciate you referring them to us. Thanks. Oh yes, and next month, so normally this runs on the third Wednesday of the month, but next month, especially related to this poster here, the Startup Edmonton has asked us to move it to October 23rd in line with Startup Week, and we will have 2 startup presentations that day. Yeah, everything? Awesome. Okay, thanks for coming.